Before I fell sick, we were discussing about plane waves. So, almost the theory we have seen. What is plane wave and what is the theory of plane wave, equations for plane wave. Then we have seen how it satisfies Maxwell's equation, then solution of Maxwell's equation for plane wave. In that, we saw that the plane wave is a fictitious wave because of conservation of energy, but plane wave is a very useful wave for analysis purpose. Therefore, we need to develop some concepts in plane wave. So today what we'll do is we'll develop some concepts in plane wave. We'll start with where we left. So I'll revise something that we discussed in the when we took when I was taking leave. So I will discuss something, then or revise something, and some part. Then we'll proceed further. Now, since we are considering plane wave, remember a few things about plane wave. First is we are considering a wave whose wave front gives us a plane. That is point one. This plane extends to infinity in both the directions. That is point two. This plane exists in a medium which is source free. There is no source in the medium, so it is source free. The medium is isotropic and the medium is homogeneous. So these are the three conditions. Medium is isotropic, homogeneous, source free, and the phase front is a plane. So the phase front of the wave is a plane. On this plane, when we say phase front represents the locus on which the phase remains constant. So on this plane, the phase is constant. The phase of the wave, if we measure the phase of the wave on this plane, that phase will remain constant. And now, what will be the phase? The phase is equal to k dot r. K is a vector called wave vector, and r is the position vector. So position vector means take any point on the plane. Then on there, if I take any point on the plane, then the position vector of that point is r. Now look at this figure. In this figure, we have taken a plane which is propagating from the origin O. It is propagating outward in the direction that is shown by the arrow. The orange arrow shows the direction in which the plane is propagating. The plane is the shaded portion is the plane that is propagating along this direction, along the direction of the arrow. And as I have told you, on this plane, if you take any point and from that point on the plane, you drop a perpendicular onto the orange line, that perpendicular will meet on the orange line at the point A. Any point on this plane which has coordinate x, y, z, x and y and z, they can be anything, but they must be on this plane. So any point on B, B has coordinates x, y, z. So the position vector of the point B is r. So r will be equal to x cap x plus y cap y plus g cap g. So that will be what is r. So from that you drop a perpendicular on to meet the orange line. that will meet the orange line, orange arrow at a point A, then the distance from the origin to A is called the projection of the vector R onto this orange line. So this distance OA will be the projection of the vector R onto the orange line or onto the direction of the wave propagation. The wave is propagating along the orange line. K is called the wave vector. We have seen this. Now, this will give us the field. The form of the field will be E is equal to E tilde into exponential j omega t. Since it is a plane wave, we have seen already that plane wave, it is a plane electromagnetic wave and it is a monochromatic wave. Since it is a monochromatic wave, plane electromagnetic wave, monochromatic wave, a monochromatic wave is a time harmonic wave. If it is a time harmonic wave, its time harmonic variation or time variation is of the form exponential j omega t plus minus j omega t. So usually we give the field E will be some constant into exponential j k dot r minus omega t. Now exponential minus j omega t is the temporal part. So if we take that out, then on the rest of the part we call E tilde. Therefore E tilde will be equal to E0 exponential jk dot r. And k dot r is the phase of the field on this plane. E0 is the amplitude part and k dot r gives us the phase on this plane. Now this field E tilde, this must satisfy the wave equation. The wave equation is del square E tilde plus omega square by V0 square E tilde is equal to 0, where E tilde is the spatial part. And why we are taking this? Why we are not taking the temporal part? Because we know the temporal part varies as exponential minus j omega t. So that part we are not taking. Now we are interested in the spatial variation or variation in the space. We are interested in that. Therefore, the spatial variation of the E field is E tilde, and E tilde must satisfy the wave equation as well as E tilde must satisfy the Maxwell's equation. So if it satisfies the Maxwell equation, then for the Faraday's law, the Maxwell equation is for E minus j omega b tilde is equal to 0. Now, from where we get this minus j omega? As you know, for monochromatic wave or for time harmonic wave, dou by dou t is equivalent to j omega. So since dou by dou t is equivalent to, dou by dou t is equivalent to j omega, so using that we get del cross E tilde minus j omega b tilde is equal to 0. So these are the two equations which must be satisfied by the plane wave. Now, from the second equation, Maxwell's equation, which is the Faraday's law, we can say B tilde is equal to 1 upon j omega into del cross E tilde. That we can easily say. So that we can write as 1 by j omega. Then as you know, if you take two vectors A and B, then A cross B is equal to x cap, y cap, g cap, and ax, b, ay, az, and bx, by, bg, determinant of these three rows. So here del is x cap dou by dou x plus y cap dou by dou y plus g cap dou by dou z. Therefore, del cross E tilde will be x cap, y cap, g cap, dou by dou x, dou by dou y, dou by dou z. Then the third row is ex tilde, ey tilde, ez tilde. This is how we can write. Now we have to find out what is dou by dou x, dou by dou y, and dou by dou z. So let us find out what is dou by dou x. Let's start with dou by dou x. So dou by dou x, if it operates on E tilde, so that will give us dou E tilde by dou x is equal to dou by dou x of E0. E0, as you know, E tilde, as I have told now, just now, E tilde is equal to E0 exponential j k dot r. So for that we will write now E0 exponential j k dot r. Now j remains as it is, k dot r, k is equal to x cap kx plus y cap ky plus j cap kj. Similarly, r is equal to x cap x plus y cap y plus g cap j. So therefore, k dot r will be x kx plus y ky plus g kj. So therefore, dou E tilde by dou x will be equal to dou by dou x operating on E0 into exponential j x kx plus y ky plus g kj. Now E0 is a constant. Then with respect to x, y, ky, g, kg, these are constant. Kx is also constant. So therefore it will operate, the differential operator will operate only on exponential j x kx. If it operates on that, that will give us j kx e to the power x exponential j x kx. So using that differential property, this differentiation dou E tilde by dou x will be equal to j kx E0 into exponential j x kx plus y ky plus g kj. Now E0 exponential of j x kx plus y ky plus j kj is equal to E0 into exponential j k dot r, which is equal to E tilde. Therefore, dou E tilde by dou x is equal to j kx E tilde, which means the differentiation, partial differentiation with respect to x, and that operating on E tilde is same as multiplying E tilde with j kx. So therefore, dou E and dou by dou x operator is equivalent to j kx. Similarly, operator dou by dou y is equal to j ky, and operator dou by dou z is equal to j kg. Now let us use this dou by dou x, dou by dou y, and dou by dou z in the expression for b tilde. Now b tilde is equal to 1 by j omega into determinant of x cap, y cap, g cap, dou by dou x, dou by dou y, dou by dou z, ex tilde, ey tilde, eg tilde. Now for dou by dou x, we'll write jkx. For dou by dou y, we write jky. For dou by dou z, we write jkg. So if you write that way, then b tilde is equal to 1 by j omega, determinant of x cap, y cap, g cap, then jkx, jky, jkg, then ex tilde, ey tilde, and eg tilde. So that we can write as 1 by j omega remains as it is. Now this one is equivalent to jk cross e tilde, because jk is the vector which is, or k is the vector which is equal to x cap kx plus y cap ky plus g cap kj, that is in the middle row. Then e tilde is equal to x cap ex tilde plus y cap ey tilde plus g cap eg tilde, which is in the bottom row. So it is product, cross product of k cross e tilde. J is multiplied with k, therefore it will be like this. So b tilde is equal to 1 by j omega into jk cross e tilde. So now let us write down b tilde, that we know is equal to 1 by j omega del cross e tilde. Now we have found out B tilde is equal to 1 by j omega into jk cross E tilde. Compare these two. 1 by j omega del cross E tilde is equal to 1 by j omega jk cross E tilde. If I compare these two, then we can easily say that delta operator is equivalent to jk. So operation on using delta is equivalent to multiplying with jk. So delta operator is equal to jk. Now you get delta operator is equal to jk. Remember, this is valid only for time harmonic fields, and that is the first condition that we have taken. It has to be time harmonic field. Field must be in isotropic, homogeneous medium, and source-free medium. So time harmonic, isotropic, source-free, homogeneous medium. Time harmonic field and medium has to be homogeneous, isotropic, and source-free. Under that condition, delta is operating with delta is same as instead of delta you can use equivalently j into k. We do not know what is k right now. We do not know what is k. We find out what is k. Now, so delta is equal to j into k. Now, the fields must satisfy the Maxwell's equation. So B tilde, E tilde, all these are going to satisfy the Maxwell's equation. Now, in a source-free region, you know divergence of E is equal to 0 in a source-free region. Therefore, divergence of E tilde is equal to 0. Now, for delta, we can write jk. So, jk dot E tilde is equal to 0. If jk dot E tilde is equal to 0, j is not equal to 0. Therefore, k dot E tilde is equal to 0. K is a vector, E tilde is a vector. Two vectors, their dot product we are taking, and their dot product is giving us 0, which means these two vectors are perpendicular to each other. So, vector k is perpendicular to vector E tilde. This in technical term is called that k and E are orthogonal to each other. So k is perpendicular to E tilde or k is orthogonal to E tilde. Similarly, we know divergence of B tilde is equal to 0. So since divergence of B tilde is equal to 0, we can say jk dot B tilde is equal to 0. J is not 0. So k dot B tilde is equal to 0. That implies that k is perpendicular to B tilde. So k is perpendicular to E tilde and k is perpendicular to B tilde. But what is k? K is the wave vector, or k gives the direction of propagation of the wave. So k gives the direction of propagation of the wave, and to the direction of propagation on the vector E tilde is perpendicular, vector B tilde is perpendicular, which means the electric field and magnetic field both are perpendicular to the direction of propagation, which means both E and B, both the fields are transverse to the direction of propagation. The direction of propagation k and the fields are transverse to each other. So electric field and magnetic field are transverse to the direction of propagation. This is called the transversality condition. So k is perpendicular to E tilde, k is perpendicular to B tilde. This is called the transversality condition. Now we know from this that k is perpendicular to E tilde and B tilde, which means E tilde and B tilde both must be perpendicular to k, which means E tilde and B tilde must be in one plane, and that plane must be perpendicular to k. So there is one plane which contains B tilde and E tilde. Since the electric field and magnetic field are contained in one plane, we call it also plane wave. So in the plane wave, the electric field and magnetic field are in one plane. Now, up to now, we have not told what is the relation between electric field and magnetic field in terms of their direction. So now let us find out what is the relation between electric field and magnetic field in terms of their direction when they are in one plane. They are in one plane. Now let us find out what will be their relation. Now B, as you know, B tilde is equal to 1 by j omega into jk cross E tilde. So that is what is B tilde. Now if you look at both the sides, on the right hand side we have a vector cross product. So it is of the form C is equal to A cross B into some scalar quantity. Scalar quantity here is 1 by omega. J will cancel out, scalar quantity will be 1 by omega. So forget the scalar quantity. So B tilde is equal to 1 by omega K cross E tilde. It is of the form C is equal to A cross B. If C is equal to A cross B, then we know from vector analysis that C will be perpendicular to A, C will be perpendicular to B. So here B tilde is K cross E tilde. So B tilde will be perpendicular to K, that we have already seen. Also B tilde will be perpendicular to E tilde. So B tilde is perpendicular to E tilde, or B tilde is orthogonal to E tilde. So B tilde, E tilde are in one plane. They are orthogonal to each other, and that plane is transverse to the direction of propagation K. Therefore K, E tilde and B tilde, they form a triad. What is triad? Triad means E tilde, B tilde and K can be represented along the principal axis of a Cartesian coordinate system. So you can see here in the figure, we have shown a Cartesian coordinate system. In the Cartesian coordinate system, in the figure you can show we are showing a Cartesian coordinate system. In the Cartesian coordinate system, along the axis, along x-axis, y-axis and z-axis, we have B tilde, E tilde and K. So they can be along any axis. So K can be along X, K can be along Y, K can be along Z. Similarly, E tilde can be along X or Y along Z, or B tilde can be along X or Y or Z, but they have to be along one axis, one of the axis, and they must satisfy this transversality condition. E tilde and B tilde must be perpendicular to each other. They must be in one plane. So, okay, next. Now, we'll come to the solution of the plane wave and dispersion relation and period. Then we'll take a break. Now, we satisfied the wave E tilde must satisfy the wave equation del square E tilde plus omega square by V0 E tilde is equal to 0. And we have seen the form of E tilde is equal to E0 exponential jk dot r. Now if I put that plus omega square by V0 square into E tilde is equal to 0. Now E tilde is not equal to 0. That is the field that is not equal to 0. Since E tilde is not equal to 0, so K square is equal to omega square by V0 square. You know, V0 is called the intrinsic velocity of the medium. So in the medium, the velocity is V0. So K square is equal to omega square by V0 square, from which we can say K is equal to omega by V0. Then intrinsic velocity V0 is equal to 1 by root over of mu epsilon, where mu is equal to mu 0 mu r, epsilon is equal to epsilon 0 epsilon r. In free space, mu r is equal to 1, epsilon r is equal to 1. So V0 is equal to C in free space. Otherwise, it will be root over of 1 by root over of mu epsilon. So therefore, K will be equal to omega into root over of mu epsilon. And we already have seen that amplitude of K or magnitude of K is equal to beta. So therefore K is equal to omega by V0, which is equal to omega root over of mu epsilon, which is equal to beta. This relation is called the dispersion relation, and it shows how K or beta varies with omega or frequency. Omega is the angular frequency. It shows how it varies with angular frequency. The angular dependence of K or beta on angular frequency is given by dispersion relation. Remember that in electromagnetics, always dispersion means variation with frequency. So the distribution over frequency, how it is distributed over frequency, gives the dispersion. How is dispersed in frequency? Now let us look at from this. Let us look at some concept for the wave. Now the wave is propagating and in space, and it is varying with time. Wave is periodic in time, it is propagating in space. To understand this, let us consider a circle. On this circle, start at any point. So starting point is 0. When you start at that point, the angle is 0. And if you complete one complete cycle along the perimeter of the circle, come back to that point, then we cover a total angle of 2 pi. So 0 from 0 we go to pi by 2, then pi, then 3 pi by 2, then we come back to 2 pi. So 0 and 2 pi are same. Again you can take another cycle, that will be 4 pi. So that way we are completing it. Now if I consider this motion, then I say it to be periodic with a period capital T, provided the time in this period, capital P, T period, in this period, if I multiply omega, omega is the angular frequency. So how much, which is in circular motion, omega is equivalent to velocity. So V into T will give you 2 pi. So total angle traveled is 2 pi. Time taken is T. Then the angular frequency is omega. Then omega into time taken gives you the total angle traveled. So the total angle traveled is 2 pi. Time taken is T. Angular frequency is omega. So omega T is equal to 2 pi. From that you can say T is equal to 2 pi by omega, or omega is equal to 2 pi by T. So this is considering the temporal progress or time. Now let us consider the spatial progress. In the spatial progress, what has happened is we have traveled one complete cycle. One complete cycle is equivalent to one wavelength. So we have traveled one wavelength that covers 2 pi distance. So lambda into the K will give you 2 pi. So in the spatial progress, K into lambda, lambda is the total wavelength, so total distance covered. Total distance covered is lambda, and that into K is equal to 2 pi. K is the wave number. Actually that into beta, beta into lambda is equal to 2 pi, but beta is equivalent to K. So since we know beta is equal to K, I can write K into lambda is equal to 2 pi. From that you can say K is equal to 2 pi by lambda, and K is equal to 2 pi by lambda, or lambda is equal to 2 pi by K. So with this we will take a break here. I will take some breaks. Today I will need more breaks. So we'll take a break. We'll come back after 10 minutes and start from the rest of the part.